Hello everyone. Today we are going to learn 8.2 area of a surface of revolution. So firstly, I'm going to draw a graph and let you know what we are going to do today. Okay. So same as before for the revolution, we have a function. For example, we have function y equals fx, and we rotate this about this case. Okay. For example, if firstly we do x-axis, and we get a revolution, so look like this, right? And in the first week, we learned how to find the volume of this revolution. Today, we are going to find area of revolution. Okay, so what's the surface area? We should say surface area. So let's see. Firstly, let's take a look at the idea. We cut this into like a small pieces, like this way. Okay. Like a same as when we find the volume. So here we are going to use this way. So the total surface area going to be the limit summation of each small piece. So if this is S piece, so we are going to find SI. What's the surface area for this small piece? And then we add them together, do the Riemann sum, and we can change the Riemann sum into definite integral. Okay, that's the idea. So how to find that surface area? Firstly, let's take a look at the cylinder, cylindrical cylinder. If we have a cylinder with height h, radius r, okay, so what's the surface area for this what's the surface area for this cylindrical cylinder? Think about calculus 1. When we learned calculus 1, we did the optimization problem. That means we want to use the least material to build a certain volume problem. Do you still remember that kind of problem? So what's the surface area? Let's have a review. Okay, we can cut, the cylinder, and then we unroll this, and we can get a rectangle, right? Like this. And here we still have the h is the height, but the length of the rectangle should be the length here should be 2 pi r, right? When we cut this, so what's the surface for this one? We can write down this is 2 pi r h, because for the rectangle is width times length. Next, let's take a look at the cylindrical core. So let's see the graph. Here we have the core, and we are going to have a look at this piece, the lower part. So here we say the radius is r1, and here the radius is r2, and the length of the side, this piece, the blue color, like this one, is L. Okay, so what's the surface area of this one? Similar to the cylindrical, it's also like a 2 pi RH, but for this one, it's going to be 2 pi, it's going to be RL, similar to the cylinder. And what's the R here? In this case, this is the average radius of the band. Okay, and also you can think another way. When we cut the whole revolution into small pieces, if we look at the graph, we cut this into small pieces because they are so close, the two slices are so close, we can look at the band, thing just look like a cylinder, right? Very close to cylinder. So it's kind of like, so here's HOL, we can say this is L, and here is the average radius. Okay. Now let's see. What's the surface area for that SI? The SI for this case, I'm going to write down here and then copy this below. So SI, just look this as same as the band. So it's 2 pi r l, right? And r is the radius. But for this situation, r is also the y value of the function. So we can write down 2 pi fxi. And then l, we say this is li. Li is the arc length of the decimal piece. Okay, so now let's see. I'm going to write down same thing here. Let's write down SI. SI, which is 2 pi fxi and li. And what's the meaning of them? This is the radius, and li is the arc length of the S piece. Okay, and let's further to change the arc length into the formula we learned in 8.1. 8.1 is arc length section, right? Do you still remember the formula for the arc length? Square root 1 plus derivative of the function and square it. Yeah, right? So this is like the arc length. So now let's write down our total surface area. S equals to limit summation of all the SI, which is limit summation of 2 pi fxi square root 1 plus derivative square and I from 1 to n goes to limit. And we did this a lot of times. We know this is a Riemann sum. We can change this into definite integral, right? So here, if f is from a to b, we set those two into the integral sign and the 2 pi fx. And here we just change all the xi into x. So f derivative square. Okay, actually for the arc length, we also have delta x. Because when we do the integral, we do have dx, right? Delta x. And here we have dx. So that's the formula for the area of surface of the revolution. Now let's take a look at the definition. Okay, so firstly, the function has to be positive. The function fx is greater than 0 is continuously differentiable. Usually when we say continuous differentiable means this surface is smooth. Okay, so here we don't talk too much about the theoretical thing, but that's the meaning. Then the area of the surface by revolving the graph of the function about x-axis is later we're also going to find area rotate about y-axis. So about x-axis is given by this one. So we write down S as surface area, and then definite integral a to b. And here we have 2 pi, and r is the y value, which is the function, and then arc length, which is we learned in 8.1, 1 plus f prime x squared dx. Okay, so basically in this section, we're just going to learn two formulas. One formula is the rotation about x-axis, The other one is rotation about y-axis. Now let's take a look at the example. Example 1. Find the area of the surface generated by revolving the curve y equals 2 root x. So about x-axis. Now firstly, let's draw the graph. 2 root x look like this one, x and the y. And then we rotate this about x-axis. So in the future, actually the graph is not necessary, but here we just want to take a look. See. Now let's set up the definite integral. Surface area equals to, we should have a to b, 1 to 2, and then 2 pi. And the radius, which is the function, right? Which is the function is, okay, firstly I can write down the formula. 1 plus derivative of the function square dx. Actually here is just the arc length. In the future, calculus 3, you will see sometimes we also make this into ds, which is small part of the arc length, ds. But here we can just, use the arc length formula. Okay, now let's plug in. Before we plug in, we can calculate what's the derivative of the function. I'm going to write that here. Derivative of the function should be 2 root x derivative. Okay, 2 is constant. Derivative of square root x should be 1 over 2 root x. 2 cancel. So this should be 1 over square root x. That's the derivative of the function. Now let's plug in. 1, 2, 2, 2 pi, function 2 square root x, and square root of 1 plus, right? 1 plus derivative square, and derivative is on the right side. Derivative square should be 1 over x, and then dx. We want to evaluate this integral, but we learned the technique of integration. Firstly, we want to simplify. So I'm going to simplify, combine those two terms together. So how to combine them? Because they both have the square root, we can just put them into one square root. And here should be 4 pi. So I'm going to take the 4 pi to the front because it's just totally constant. We don't need them. Now, to 4 pi and the square root of x times 1 plus 1 over x dx. Right? And simplify. Square root x plus 1. This looks familiar, right? We did this in arc length section. We should use u sub. So u should be x plus 1. And for this case, it's du just dx, which is easy case, but we need to change the bound. So x is 1, u is 2, x is 2, u should be 3. Okay, so for this case, we should have 4 pi 2 to 3 square root u du, right after the u sub. And now we just evaluate this number. So which is 4 pi. Here should be u 3/2 and 2/3 in front, u from 2 to 3. Let's simplify. So here 8 pi over 3, and we just plug in the upper bound, the lower bound. We don't need to simplify. Minus 2 to the 3/2. So that's the arc length of, not arc length. This is the surface area of this revolution. Okay. Now we can try exercise problem. So even this is like a synchronized class, but I still suggest you to pause my video and do the problem by yourself, because we need the practice, right? Without my instruction, you just copy my example and see if you understand the surface area problem. Okay, you know how to do this. I will give you the solution later. Here's the solution. So you can take a look. Firstly, I calculate the derivative of the function, and then I just plug into the formula 0 to 1, 2 pi, the function fx, and the arc length function. Okay, arc length like a formula, right? And then when I simplified, I factor constant out. No, I noticed we have x to the fourth and we have x to the third, so it should be the u sub problem. So I did the u sub u equals 1 plus 9x to the fourth, and then change the bound and just simplify. It's exactly the same as the example problem. And then after evaluate, the final answer is pi over 27, 10 to the 3 half minus 1. So this is the revolution about x-axis. So I'm going to do y-axis, rotation about y-axis on Monday. You can stop here for Friday's lecture.